So in 5.4, we're going to talk about the fundamental theorem of calculus. So there's two main parts to it and then sort of a little part of it as well. So first we'll talk about the derivative part of it. So if f is continuous on a closed interval from a to b, then the function capital F of x, which is defined as the integral function from a to x of little f of t dt, has a derivative at every point c in the interval from a to b, and that derivative, capital F prime, is the derivative of that integral function is just f of x. So I'll do an example of y right here. So with the integral of cosine of t, we know that first I'm going to say that's the derivative of, and we can actually do this integral. So the integral of cosine is sine, and if we evaluate that from negative pi over 3 to x, that would be the sine of x minus the sine of negative pi over 3. So that would mean we're taking the derivative of sine of x, let me make that a derivative of sine of x, and then sine of negative pi over 3 is going to be a square root of 3 over 2, I believe. So that will be a minus square root of 3 over 2. So when we differentiate that, the derivative of sine takes us right back to cosine of x, and no matter what this was, its derivative, the derivative of a constant, is going to be 0. So our shortcut version, what we're trying to convince ourselves, is that when we differentiate this integral function, what we get is the integrand evaluated at x. So that means now also, so if we said the integral of something that we couldn't integrate, say we go from 5 to x, and we're going to try to take the derivative of sine of t squared dt, there is no closed form integral of sine of t squared, but if we believe what we have just said here, the derivative is going to be, we're just going to plug the x in there and remove the integral sign, so it's going to be sine of x squared. So this, the power of the fundamental theorem of calculus, the derivative part, is not in differentiating something that we could already find an integral of, plug in, and then do the derivative. It's, can we take a derivative of something that we can't integrate? Now, we can also do this, we'll see the chain rule as applied to this. So on the next one, we know that we're going to take the derivative. I'm going to work this out again by finding the antiderivative first, then differentiating, and then we'll see what that means. So again, the integral of cosine is sine, and when we evaluate that at the upper limit, minus evaluate that at the lower limit, then we're going to get a chain rule derivative for sine of x squared. So the derivative of sine is going to be cosine of x squared, and then we're going to take the derivative of the inside function, which is this part right there, and it doesn't matter what we evaluated this at, that's just going to be a constant, so its derivative is going to be 0. So what we see though is this chain rule derivative from the fundamental theorem of calculus. So on the next one, if the variable is in the lower limit, then what we're going to get is the constant that we would have gotten here is going to be 0, so it'll be a minus 1 over the natural log of x. And the shortcut here is we're going to get a negative because it's the lower limit that has the non-constant. We'll plug in our sine of x, so that'll be sine cubed of x plus 1 in the denominator times the derivative of sine x, which is a cosine of x. So we will get a negative cosine x over sine cubed x plus 1. And on the last one, now we have functions in the numerator and denominator. So, and they're going to be chain rule derivatives. So we're going to get, my hand keeps touching this. So we're going to find a place to rest my hand that won't make it jump. So we'll get e to the x cubed, and then we're going to get times 3x squared over, that's going to be e to the x cubed minus 1, minus plugging in the lower limit, we're going to get e to the 3x, and then times the 3 over that e to the 3x minus 1. Okay, let's go on. Now here's another part of this. We can create solutions to differential equations. So it looks something like this. We can define a function that has secant x as its derivative by taking the integral from some constant 2x of secant of t dt. So I'm going to call that my function f of x. Now, can you see that f prime of x is going to be just secant of x? And so we have satisfied this part of the differential equation. Now, we also need to have this, the evaluation part, that f of negative 2 is 7. So I'm going to choose that a value to match that negative 2. So I'm going to say that f of x is going to be the integral from negative 2 to x of secant of x. I got to choose something other than x. So secant of t dt. Now, so far, I still have the derivative is a match. The derivative of this integral function is still going to be secant of x. But now, if I evaluate this at negative 2, then the integral from negative 2 to negative 2 is 0. So I'm going to make it be 7 by adding in that 7. So now our function, 7 plus the integral from negative 2 to x of secant of t dt, will still satisfy the derivative. Its derivative is secant of x, so it satisfies that differential equation, and it satisfies the initial condition that f of negative 2 is equal to 7. So if you see how to play the game, we're going to say that our function, f of x, I'm going to leave a little space here. I'm going to go from e to x of e to the t squared dt. So now I have built an integral function whose derivative will be exactly what I want it to be. And now to make it have the right constant, the right initial condition, I'm going to add in pi there. Takes a little bit of thinking to get to there. The second part of the fundamental theorem of calculus is the integral evaluation part of it. So it says that the integral from a to b of little f of x is an antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. So, for example, we know that the integral, an antiderivative of 3x squared is x cubed, and an antiderivative of 2x is x squared, and then we can evaluate from negative 1 to 2, so that's going to be 2 cubed plus 2 squared minus negative 1 cubed plus negative 1 squared. So that looks like 8 plus 4 is 12. And then we have a negative 1 plus 1 is 0. And so we will get 12. Similarly, we can say the integral of e to the x is e to the x. Evaluate from 1 to the natural log of 5. We'll get e to the natural log of 5 minus e to the first. And an exponential based Euler's number and a logarithm based Euler's number are inverses. That's going to be 5 minus e, and that is our answer. And the integral of cosine is a sine of x, going from 0 to pi over 2 is going to be sine pi over 2 minus sine of 0. Sine of pi over 2 is 1. and the sign of 0 is 0, and so we will get 1. Okay, so we want to make a connection to the area between a curve and the x-axis. So we have to be careful because an integral is a sort of signed area. So if the curve is below the x-axis, or if we integrate from right to left, the lower limit is bigger than the upper limit, then it's going to change the sign, and it's entirely possible to get a negative answer to an integral, but an area must always be positive. So, for example, if we want to find the area, so the key is we're trying to find area between our curve and the x-axis between 0 and 1, we can see that our curve is completely above the x-axis on that interval, so we don't really have to worry. We can go ahead and evaluate this integral from 0 to 1 of 1 minus x squared. That's going to be x minus 1/3 x cubed, going from 0 to 1. So that's going to be 1 minus 1/3, and then minus the 0, and so we'll get an area of 2/3. So that is going to represent what we have on this part right here. So the yellow is the region that adds up to be 2/3. That's that area. Now the next one poses a bigger problem because this interval from 0 to 2, we're going to get part of the curve is above the x-axis and part of the curve is below. So we are interested in this area between the curve and the x-axis, but we need for it to be a true area, which means we want to consider both of those to be positives. So if you have a graphing calculator, you could go from 0 to 2 and just plug in the absolute value of 1 minus x squared dx. If we're going to, and then the calculator will give you that answer using FN integrate. If we don't have access to a calculator, we're going to have to split this integral up and go the integral from 0 to 1. That's the part where the curve is above the x-axis, where we're going to get a positive result. And then we're going to have to go minus to change the sign and go from 1 to 2 of that 1 minus x squared dx, because that's the part that's going to be below the x-axis, which if we don't do that minus is going to end up giving us a negative result, and we'll get kind of a net area instead of the true area that we're after. So we already did this part. We know that's 2/3. And so now we're going to get minus, and then we have again x minus the 1/3 x cubed that now we're going to evaluate from 1 to 2. So that's going to be negative of, and so we'll get 2 minus 2 cubed is 8/3. So there's the upper limit. Minus plugging in the 1 is going to be 1 minus 1/3. So that looks like we're going to get, let's see, 2 is 6/3. So that's going to be a negative 2/3. And then we're going to get minus, and then 1 minus 1/3 is another 2/3. And so that's going to be the negative of negative 4/3. So that's going to be a 4/3. So the area below the curve is 4/3, plus the area that was above the x-axis is going to be 2/3, giving us 6/3 or 2 for that total area between the curve and the x-axis. So it depends on how the question is framed, whether we need to worry about whether it's above or below the x-axis. Okay. Finally, we're going to now try to analyze our antiderivatives graphically. So we're looking at f of x. The green curve is f of x, and our h of x is defined as the integral from 1 to x of f of t dt. So h of 1 would mean we are going to take the integral from 1 to 1 of f of t dt, but the integral from 1 to 1 of anything is 0. So that part's not too bad. h of 0, now we have to imagine we're going to take this integral from 1 to 0 of f of t dt. Now we can see that the curve lies above the x-axis from 0 to 1, but because our limits are going from a bigger number 1 to a smaller number 0, that's going to change the sign. So the fact that the curve is above the x-axis would give us a positive result. Because we're going from positive to negative, that's going to change that and mean that we're actually going to have a negative number. H of 0 will be negative. For what values of x would we have a relative maximum? Well, we need to recognize that h prime of x is going to be f of x. That's from our fundamental theorem of calculus. And the curve we're looking at in green over here is f of x. So to find a relative max, we want to know where the derivative changes from positive to negative. And the only place we see that that happens is going to be here at x equals 4. So we will have a relative maximum at x equals 4. Now we could also say that if we're going to be careful, and I have to think about this because I'm not used to considering endpoints too, but our book does consider endpoints. So at the endpoint here, we can see that our derivative to the right of 0 is positive, and so that means wherever, if we were imagining graphing f, that since its derivative to the right is positive, it's going to be increasing. And likewise at 8, the derivative to the left here is negative. So at that endpoint at 8, the function is going to be decreasing. So that is going to make those endpoints be relative minima, but not relative maxima. Now the absolute maximum then is going to be the largest value of f at each of those critical points and endpoints. So the critical points, the points we need to consider, are going to be where f prime of x is equal to 0. I'm sorry, h prime of x. H prime of x is equal to 0, which is going to be where f of x is equal to 0. And so that is going to be at 1, at 4, and then the endpoints 0 and 8. So those are the places we must consider. And for the absolute max, we can see that, like we said earlier, at 0, the function is going to be increasing to the right. And so that means that at x equals 1, that could not be the absolute maximum. At 0, it couldn't be the absolute maximum. At 1, it continues to increase on both sides, so it won't be the absolute maximum either. And at 4, we can see that we will have accumulated all of this area here from where we started at x equals 0, and the remainder of the way it's going to be decreasing over here. So in fact, that is going to be our absolute maximum. Let's see. So we'll say that's going to be at x equals 4. And relative minimums will be where the derivative changes from negative to positive, or possibly at endpoints. So there is no interior point where it goes from negative to positive, but we will have relative minima at both 1 and 8. And that's for the relative minima. Now the absolute minimum, so we can see that 0 is in contention. X equals 0 could be contention because that's a relative minimum. All these points on the interior, 1 and 4, because the derivative to the left was positive, they were increasing, they were accumulating more area, so those aren't going to be minima. The only other possibility is 8. And so here's our judgment call. It looks like we have gathered up more area underneath the curve from 4 to 8 than we gained with the area above the curve from 0 to 4. So my guess then is that x equals 8 is going to be the absolute maximum. Or that's not the maximum, that's where it will occur. And where does h have an inflection point? So h will have an inflection point where the h prime has a relative min or relative max. And so that's going to be at all of those mountaintops and valleys on the green curve. So that is going to be at 1, also at 3, and also at 6. All right, very good.